Alright, testing my mic again.
Using
Alright, we are getting an output on camera now. So, here's what happened. Well, nothing much to say. A power failure happened and my system shut down. So that's why my stream ended abruptly. Let's just continue from where we left off.
Pytorch.
If you're a web designer, here are 4 Wix Studio features you gotta know.
Welcome.
The audio isn't connected to my earbuds now, is it?
Back. In the last video, we saw that the model that we've been building has some potential to learn. I mean, look at these predictions. You could get a little bit better, of course, get the outdated function. One of the deep completeness practice splits. Pen that operation on means our model is y test, and then we can also calculate the test accuracy.
Yeah, that's what we're about to do. We were about to. Well, I guess now we'll have to run all now. Or maybe not. Let's just see. Okay, seems like Google Colab has a time limit for when it resets. Anyhow, so let's just scroll down. Yeah, we were about to make our predictions, and so that this bracket wasn't closed, and that's when the power failure happened. Let me turn this on. Well, I don't need all the predictions. I'm just gonna print the first 10. Same goes for our y test. Let's just print the first 10 elements. Would you look at that? Yeah, this one is wrong. But other than this one, everything else is right.
I'm just going to give myself some more space here so I can code in the middle of the screen. Equals accuracy function on what? We're going to pass in y true equals y test. And then we will pass in y pred equals and the value where manuals are. What matching y test? Always all getting here a value which is gone up, albeit not by what. Now that is the power of nonlinearity. All we did was we added in a ReLU layer, or just 2 of them. ReLU here, ReLU here. But what did we do? We gave our model the power of straight lines. Straight linear, of straight line. Plot our model's decision boundary using our function and see if it really did learn anything. I'll see you there. Welcome back. In the last video, we trained our first model, and as you can tell, I've got the biggest smile on my face, but we trained our first models and nonlinear functions. And by the 1000th epoch, we look like we're getting a bit better results than just pure guessing, which is, so we have evenly balanced function, but you play around with the lookup code. Numbers on a page. So let's write down here 6.4. What do we like to do to evaluate things? It's visualize nonlinear. Point that neural networks are really just a big combination of linear and nonlinear. Let's make our mode beautiful 3 and then pass in X test. And I actually really like that we did, because then we got to troubleshoot a shape error on the feds. We want Y, want that equals to our. The other ones look pretty good. This might look pretty good if we visualize it. So now you might have already done this because I issued the challenge of plotting the decision boundaries. Plot decision boundaries, and let's go plt.figure, and we're going to set up the fig size to equal.
It's because do we have to train our model again? I think we do need to
12.6, because again, one of the advantages of hosting a machine learning cooking show is that you can code ahead of time, and then we can go pl to call it in our grade state. Subplot is on a title.
Oh, it says model 0, that PI. And
plot.title. This will be test.
There we go.
Google
that
Colab.
looks way better, doesn't it?
As I said, this course is also a battle between me and Google Colab's autocorrect. So we're going to model on the X, the features input, and then we'll compare them with the Y values. Let's see what's going on here. Look at that! Yes! Our first nonlinear model!
I like how Daniel is always excited. Sounds always excited. Change the speed to X.
Okay, it's not perfect, but it is certainly much better than the models that we had before. Look at this. Model 1 has no linearity. Model 1 equals no non-linearity. I've got a double negative there. Whereas Model 3 equals has non-linearity. So do you see the power of non-linearity, or better yet, the power of linearity or linear straight lines with non-straight lines? So I feel like we could do better than this, though. Here's your challenge, is can you improve Model 3 to do better? What did we get?
Sure. What we have to do would be just actually let's just do it, train it for 10,000 times. Whoa, hold on a second. We reached 100% there. Okay, I get it. Yep. That's pretty good. We need to train it this many times, I believe that. Okay, anyhow. Let's now plot it, and there we go. That's pretty awesome. Our training set, and this is our testing set. You know what? I want to understand what does subplot mean though. Oh, okay. It just means so this is the huge plot with 12.6 as the figure size. This is our first plot, which is on 121. The second plot 122. And then what are we doing here? Yeah, we are passing this to the function there.
79% accuracy to do better than 80% accuracy on the test data. I think you can. So that's the challenge. And if you're looking for hints on how to do so, where can you look? Well, we've covered this, improving a model. So maybe you add some more layers. Maybe you add more hidden units. Maybe you fit for longer. Maybe if you add more layers, you put a ReLU activation function on top of those as well. Maybe you lower the learning rate, because right now we've got 0.1. So give this a shot. Try and improve it. I think you can do it. But we're going to push forward. That's going to be your challenge for some extra curriculum. I think in the next section, we've seen our nonlinear activation functions in action. Let's write some code to replicate them. I'll see you there. Welcome back. In the last video, I left off with the challenge of improving Model 3 to do better than 80% accuracy on the test data. I hope you gave it a shot, but here are some of the things I would have done, is I potentially add more layers, maybe increase the number of hidden units, and then if we needed to, fit for longer, and maybe lower the learning rate to 0.01. But I'll leave that for you to explore, because that's the motto of the data scientist, right, is to experiment. So let's go in here. We've seen our nonlinear activation functions in practice. Let's replicate them. So replicating nonlinear activation functions. And remember, neural networks, rather than us telling the model what to learn, we give it the tools to discover patterns in data, and it tries to figure out the best patterns on its own. And what are these tools? Let's write down here. We've seen this in action. And these tools are linear and nonlinear functions. So a neural network is a big stack of linear and nonlinear functions. For us, we've only got about 4 layers or so, 4 or 5 layers. But as I said, other networks can get much larger. But the premise remains, some form of linear and nonlinear manipulation of the data. So let's get out of this. Let's make our workspace a little bit more cleaner. Replicating nonlinear activation functions. So let's create a tensor to start with. Everything starts from the tensor. And we'll go A equals torch, a range. And we're going to create a range from -10 to 10 with a step of 1. And we can set the d type here to equal torch.float32, but we don't actually need to. That's going to be the default. So if we set A here, A.dtype, and we've got torch float32, and I'm pretty sure if we got rid of that, oh, we've got torch in64. Huh, why is that happening? Well, let's check out A.
Hmm. Shouldn't we get isn't float 32 the default type of you know of a tensor?
Oh, it's because we've got integers as our values, because we have a step as 1. If we
Oh, okay. So it depends on what yeah, I
turn this
see.
into a float, what's going to happen? We get float 32, but we'll keep it, otherwise this is going to be what, about 100 numbers? Yeah, no, that's too many. Let's keep it at negative 10 to 10, and we'll set the D type here to torch float 32. Beautiful. So it looks like Pytorch's default data type for integers is int64, but we're going to work with float 32 because float 32, if our data wasn't float 32, with the functions we're about to create, we might run into some errors. So let's visualize this data. I want you to guess, is this a straight line or non-straight line? You've got 3 seconds. 1, 2, 3. Straight line. There we go. We've got negative 10. The positive 10 up here, or 9. Close enough. And so how would we turn this straight line? If it's a straight line, it's linear. How would we perform the ReLU activation function on this? Now, we could, of course, call torch ReLU on A. Actually, let's in fact just plot this. plt.plot on torch ReLU. What does this look like?
Yeah, at 0 till it reaches 0, till it reaches 0.0, till it reaches 1, it's just gonna be, yeah, there we go, and it just booms, goes up.
Boom, there we go. But we want to replicate the ReLU function. So let's go nn.relu. What does it do? We've seen this before. So we need the max, we need to return, based on an input, we need the max of 0 and x. So let's give it a shot. We'll come here. Again, we need more space. There can never be enough code space here. I like writing lots of code. I don't know about you. But let's go ReLU. We'll take an input x, which will be some form of tensor, and we'll go return torch.maximum. I think you could just do torch.max, but we'll try maximum. Torch.tensor 0. So the maximum is going to return the max between whatever this is, one option, and whatever the other option is. So inputs must be tensors. So maybe we could just give a type hint here that this is torch.tensor, and this should return a tensor too. Return torch.tensor. Beautiful. You ready to try it out? Let's see what our ReLU function does. ReLU A. Wonderful. It looks like we got quite a similar output to before. Here's our original A. So we've got negative numbers. There we go. So recall that the ReLU activation function turns all negative numbers into 0 because it takes the maximum between 0 and the input. And if the input's negative, well, then 0 is bigger than it. And it leaves all of the positive values as they are. So that's the beauty of ReLU. Quite simple, but very effective. So let's plot ReLU activation function, our custom one. We will go plt.plot. We'll call our ReLU function on A. Let's see what this looks like. Oh, look at us go. Well done. Just the exact same as the torch ReLU function. Easy as that, eh? And what's another nonlinear activation function that we've used before? Well, I believe one of them is, if we go down to here, what did we say before? Sigmoid, where is that? Where are you, Sigmoid? Here we go. Hello, Sigmoid. Ooh, this has got a little bit more going on here. 1 over 1 plus exponential of negative x. So sigmoid, or this little symbol for sigmoid, of x, which is an input, we get this. So let's try and replicate this. Let's just bring this one in here. Right now, let's do the same for sigmoid.
Yep, let's do that.
Well, we want to create a custom sigmoid, and we want to have some sort of input, x.
Not really. I mean, we can just do this type. We can just do plot.plot, torch.sigmoid. I mean, yeah, he wants to create a custom function, I get it, but let's just do this first and see what we get. Yep, the results are just jam-packed between 0 and 1.
I want to return 1 divided by, do we have the function in sigmoid? 1 divided by 1 plus exponential, 1 plus torch.exp for exponential on negative x. And we might put the bottom side in brackets so that it does that operation. I reckon that looks all right to me. So 1 divided by 1 plus torch.
Return 1 divided by 1 plus we're gonna raise it to x raised to
so that
minus.
does that operation. I reckon that looks all right to me. So 1 divided by 1 plus torch. exponential of negative x. Do we have that? Yes, we do. Well, there's only one real way to find out. Well, let's plot the torch version of sigmoid. Torch.sigmoid, and we'll pass in x, see what happens. And then, oh, we have a. My bad. A is our tensor. What do we get? We get a curved line. Wonderful. And then we go plt.plot, and we're going to use our sigmoid function on a. Did we replicate Torch's sigmoid function? Yes, we did. Woohoo! Now, see, this is what's happening behind the scenes with our neural networks. Of course, you could do more complicated activation functions or layers and whatnot. You can try to replicate them. In fact, that's a great exercise to try and do. But we've essentially, across the videos and the sections that we've done, we've replicated our linear layer, and we've replicated the ReLU. So we've actually built this model from scratch.
Oh, we have Power Up again. I'm back on our stream. Hey there. How are you doing today?
If we really wanted to, but it's a lot easier to use Pytorch's layers because we're building neural networks here like Lego bricks, stacking together these layers in some way, shape, or form. And because they're a part of Pytorch, we know that they've been error tested and they compute as fast as possible behind the scenes and use GPU and get a whole bunch of benefits. Pytorch offers a lot of benefits by using these layers rather than writing them ourselves. And so this is what our model is doing. It's literally like to learn.
Doing good, doing good. Just, continuing with where we left off. So I just, yesterday we were not able to figure this part out. And now, yeah, look at this. It's separated using, the ReLU layer. Like, it doesn't use a straight line anymore. It just uses a bunch of straight lines to make this curve over here. Wow, indeed.
These values and decrease the loss function and increase the accuracy. It's combining linear layers and nonlinear layers or nonlinear functions. Where's our ReLU function? Here. A ReLU function like this behind the scenes. So just combining linear and nonlinear functions to fit a data set. And that premise remains even on our.
Oh, by the way, I made some adjustments to my mic yesterday, so hopefully my sound should be way better,
So
or at least better than what it was yesterday.
But we've worked on a binary classification problem. Have we worked on a multi-class classification problem yet? Do we have that here? Where's my fun graphic? We have multi-class classification. I think that's what we cover next. We're going to put together all of the steps in our workflow that we've covered for binary classification. But now let's move on to a multi-class classification problem. If you're with me.
Alright, it is loud enough.
I'll see you in the next video.
Alright, that's what I like.
In the last few videos, we've been harnessing the power of nonlinearity, specifically non-straight line functions, and we replicated some here. And we learned that a neural network combines linear and nonlinear functions to find patterns in data. And for our simple red versus blue dots, once we added a little bit of nonlinearity, we found the secret sauce of to start separating our blue and red dots. And I also issued you the challenge to try and improve this, and I think you can do it. So hopefully you've given that a go. But now let's keep pushing forward. We're going to reiterate over basically everything that we've done, except this time from the point of view of a multi-class classification problem. So I believe we're up to section 8, putting it all together with a multi-class classification problem. Beautiful. And recall the difference between binary classification equals one thing or another, such as cat versus dog, if you're building a cat versus dog image classifier, spam versus not spam for, say, emails that were spam or not spam, or even internet posts on Facebook or Twitter.
Now we're moving over to multi-class classification. So we just finished binary classification, and now is this the next step?
One of the other internet services, and then fraud or not fraud for credit card transactions, and then multi-class classification is.
Hey, look at that! We have a third viewer right now. Hi to us watching.
So I think we've got all the skills to do this. Our architecture might be a little bit different from a multi-class classification problem, but we've got so many building blocks now, it's not funny. Let's clean up this, and we'll add some more code cells. And just to reiterate, so we've gone over nonlinearity. The question is, what could you draw if you had an unlimited amount of straight, linear, and non-straight, nonlinear lines? I believe you could draw some pretty intricate patterns, and that is what our neural networks are doing behind the scenes. And so
we also can draw literally anything with that.
Some of the ones that we've used before, we could create a range. Linear activation is just the line itself, and then if we wanted to do sigmoid, we get this curl here. And then
yep, a call that like whatever number we give inside sigmoid just squishes it between 0 and 1. And then we have our ReLU function. We just if we give it a negative number, it just outputs 0, else it gives the positive number back.
If we wanted to do ReLU, well, we saw
machine learning is I think machine learning is at least the only field in programming and software engineering that have come so far where we actually end up using math, or we need understanding of math to make things work.
ReLU function is one. These both are nonlinear, and of course Torch.nn has far more nonlinear activations where they came from, just as it has far more different layers. And you'll get used to these with practice, and that's what we're doing here. So let's go back to the keynote. So this is what we're going to be working on, multi-class classification. So there's one of the big differences here. We use the softmax activation function versus sigmoid. There's another big difference here. Instead of binary cross entropy, we use just cross entropy. But I think most of it's going to stay the same. We're going to see this in action in a second, but let's just describe our problem space. Just to go visual, we've covered a fair bit here. Well done, everyone. So binary versus multi-class classification. Binary, one thing or another, 0 or 1. Multi-class could be 3 things, could be 1,000 things, could be 5,000 things, could be 25 things. So more than one thing or another. But that's the basic premise we're going to go with. Let's create some data, hey? 8.1. Creating a tawny multi-class dataset. And so to create our dataset, we're going to import our dependencies. We're going to re-import Torch, even though we already have it, just for a little bit of completeness. And we're going to go matplotlib, so we can plot. As always, we like to get visual.
So yeah, I guess this is the next part of it.
Where we
We're
can
gonna create multi-class
visualize.
dataset.
We're going to import from scikit-learn.datasets. Let's get make blobs. Now, where would I get this from? So sklearn.datasets, what do we get? Koi datasets.
All right, let's just open that up. Sets. So I have quite a lot of datasets now on there.
Do we have classification? Koi datasets. Do we have blobs?
Maybe I'm looking at the wrong thing.
Or if we just go make scikit-learn classification datasets. What do we
Make scikit-learn classification datasets.
get? Here's one option. There's also make blobs. Beautiful. Make blobs. This is the code for
Make blobs. Isn't blob the paragraph equivalent in SQL? Maybe it has another meaning in scikit-learn and machine learning.
that. So let's just copy this in here and make blobs. We're going to see this in action anyway. Make blobs. As you might have guessed, it's make some blobs for us. I like blobs. It's a fun word to say, blobs. So we want train test split because we want to make a data set and then we want to split it into train and test. Let's set the number of hyperparameters. So set the hyperparameters for data creation. Now, I got these from the documentation here. Number of samples, how many blobs do we want, how many features do we want? So say, for example, we wanted 2 different classes. That would be binary classification. Say, for example, you wanted 10 classes, you could set this to 10, and we're going to see what the others are in practice. But if you want to read through them, you can well and truly do that. So let's set up. We want num classes. Let's double what we've been working with. We've been working with 2 classes, red dots are
All right. So maybe we have other color dots too in this
blue
case,
dots.
I
Let's
guess.
step it up a notch. We'll go to 4 classes. Watch out, everyone. And we're going to go number of features will be 2. So we have the same number of features. And then the random seed is going to be 42. You might be wondering why these are capitalized. Well, generally, if we do have some hyperparameters that we say set at the start of a notebook, you'll find it's quite common for people to write them as capital letters just to say that, hey, these are some settings that you can change. You don't have to, but I'm just going to introduce that anyway because you might stumble upon it yourself. So create multi-class data. We're going to use the make blobs function here. So we're going to create some X blobs, some feature blobs, and some label blobs. We'll see what these look like in a second. I know I'm just saying blobs a lot. But we pass in here, none samples. How many do we want? Let's create 1,000 as well. That could really be a hyperparameter, but we'll just leave that how it is for now.
Make blobs. Number of samples. Just 2,000.
Number of features is going to be num features. Centers equals num classes. So we're going to create 4 classes because we've set up num classes equal to 4. And then we're going to go center, standard deviation. We'll give them a little shake up, add a little bit of randomness in here. Give the clusters a little shake up. We'll mix them up a bit, make it a bit hard for our model. But we'll see what this does in a second. Random state equals random seed, which is our favorite random seed, 42. Of course, you can set it whatever number you want, but I like 42. Oh, and we need a comma here, of course. Beautiful. Now, what do we have to do here? Well, because we're using scikit-learn, and scikit-learn leverages NumPy.
Gives the classes a little shake up, meaning they would be just they're not in the center. Is that what it means? Will just be randomized all around, I believe.
So let's turn our data into tensors. Turn data into tensors. And how do we do that? Well, we grab xblob and we call torch from NumPy. From NumPy, if I could type, that would be fantastic. That's all right. We're doing pretty well today. Haven't made too many typos. We did make a few in a couple of videos before, but hey, I'm only human. So we're going to torch from NumPy, and we're going to pass in the yblob, and we'll turn it into torch.float, because remember NumPy defaults as float64, whereas Pytorch likes float32. So split into training and test, and we're going to create xblob train, y or x test, xblob test. We'll keep the blob nomenclature here, y blob train and y blob test. And here's again where we're going to leverage the train test split function from scikit-learn. So thank you for that scikit-learn. X blob, and we're going to pass the y blob, so features, labels, x is the features, y are the labels, and a test size. We've been using a test size of 20%. That means 80% of the data will be for the training data. That's a fair enough split with our data set. And we're going to set the
Or we need to make a device agnostic though.
Random seed to random seed, because normally train test split is random, but because we want some reproducibility here, we're passing random seeds. Finally, we need to get visual. So let's plot the data. Right now we've got a whole bunch of code and a whole bunch of talking, but not too much visuals going on. So we'll write down here, visualize, visualize, visualize. And we can call in plot.figure. What size do we want? I'm going to use my favorite hand poker, which is 10.7, because it's generally worked out to be a good plot size, in my experience anyway. We'll go xblob, and we want the 0th index here, and then we'll grab xblob as well. And you might notice that we're visualizing the whole data set here. That's perfectly fine. We could visualize train and test separately if we really wanted to, but I'll leave that as a little challenge to you. And we're going to go red, yellow, blue. Visualize train index here, and then we'll grab xblob as well. And you might notice that we're visualizing the whole data set here. That's perfectly fine. We could visualize train and test separately if we really wanted to, but I'll leave that as a little challenge to you. And we're going to go red, yellow, blue. Wonderful.
Take up that.
What did we get wrong? Oh, of course we got something wrong. Center STD. Did we spell center wrong? Cluster STD. That's what I missed.
It's not. It's cluster.
So cluster STD. Standard deviation. What do we get wrong? Random seed. Oh, this needs to be random state. Oh, another type. You know what? Just as I said I wasn't getting too many typos, I get 3. There we go. Look at that.
What did I do wrong here? Found input variables with inconsistent number of samples. Blob by blob. Then you convert it from numpy and make it okay. So xblob
This needs to be random.
train test blob blob where test random C and random state all good.
State. Oh, another typo. You know what? Just as I said I wasn't getting too many typos, I get 3. There we go. Look at that.
Well, the graph looks as predicted, but what's the error that I have on my side? Found input variables with inconsistent size of samples, so probably something to do with the indexing is my guess. Did I do xblob 2 times?
Wonderful.
That is supposed to be xblob 2 times, isn't it? This is the x coordinate and this would be the y coordinate. What is happening here?
Hey, I'm going to type in data. Now, what do we have to do here?
4242.
Well, because we're using scikit-learn and scikit-learn leverages NumPy. So let's turn our data from NumPy, if I could type, that would be fantastic. That's all right. We're doing pretty well today. Haven't made too many typos. We did make a few in a couple of videos before, but hey, I'm only human. 64, whereas Pytorch likes float 32. So split into training and test, and a blob train and y blob test. And here's again where we're going to leverage the train test split function from scikit-learn. So thank you for that, scikit-learn. X blob, and we're going to pass the y blob, so features, labels, X is the features, Y are the labels, and a test size. We've been using a test size of 20%. That means 80% of the data will be for the training data. That's a fair enough split with our data set. And we're going to set the random seed to random seed, because normally train test split is random, but because we want some reproducibility here, we're passing random seeds. Finally, we need to get visual. So let's plot the data. Right now we've got a whole bunch of code and a whole bunch of talking, but not too much visuals going on. So we'll write down here, visualize, visualize, visualize. And we can call in plot.figure. What size do we want? I'm going to use my favorite hand poker, which is 10.7, because it's generally worked out to be a good plot size for my experience anyway. We'll go X blob, and we want the 0th index here, and then we'll grab X blob as well. And you might notice that we're visualizing the whole data set here. That's perfectly fine. We could visualize train and test separately if we really wanted to, but I'll leave that as a little challenge to you.
So let's just look at what the error says. Found input variables with inconsistent number of samples. Google that now. Hmm. Let's just do X blob and Y blob, the first 10 entries. And there we go. Oh, it's in here that we're getting the error. Okay, what does it say? Found input variables with inconsistent number of samples. Hmm. Let's print it before and see what we get. You know what? Let's just comment all that lines out, those lines out, and see. Ah, do you see that? Instead of a period, we put a comma there, and apparently torch.float would change the dimensions in that case. Anyhow, let's just plot them again. This time it should work, and it did work. There we go. What happens if we put the number of classes, increase that? Please put it as 9. Okay, let's just change it back to what it was.
To you, and we're going to go red, yellow, blue. Wonderful. What did we get wrong? Oh, of course we got something wrong. Center STD. Did we spell center wrong? Cluster STD. That's what I missed. So cluster STD. So I suppose I get 3. There we go, between all of the dots. Now if we set this cluster STD to 0, what happens? We get dots that are really just, look at that. That's too easy. Let's mix it up, all right? Now, you can pick whatever value you want here. I'm going to use 1.5 because now we need to build a model that's going to draw some lines between these 4 colors, 2 axes, 4 different classes. But it's not going to be perfect because we've got some red dots that are basically in the blue dots. And so, what's our next step? Well, we've got some data ready. It's now time to build a model. So, I'll see you in the next video. Let's build our first multi-class classification model.
Let's do that.
In the last video, we created a multi-class classification dataset using scikit-learn's makeblobs function. And now, why are we doing this? Well, because we're going to put all of what we've covered so far together. But instead of using binary classification or working with binary classification data, we're going to do it with multi-class classification data. So with that being said, let's get into building a multi-class classification model. So we'll create a little heading here. Building a multi-class classification model in Pytorch. And now, I want you to have a think about this. We spent the last few videos covering nonlinearity. Does this dataset need nonlinearity? As in, could we separate this dataset with pure straight lines? Or do we need some...
I mean, this data set, in a way, we can separate it with linear lines, right? Because to separate the blue, we just draw a straight line here. Yellow, we can just draw a straight line here. Red and blue is a bit tricky, but even if we draw a straight line, it isn't as if we lose out on a lot of percentage or
some non-straight lines as well. Have a think about that. It's okay if you're not sure. We're going to be building a model to fit this data anyway, or draw patterns in this data anyway. And now, before we get into coding a model, so for multi-class classification, we've got this. For the input layer shape, we need to define the in features. So how many in features do we have? For the hidden layers, well, we could set this to whatever we want, but we're going to keep it nice and simple for now. For the number of neurons per hidden layer, again, this could be almost whatever we want, but because we're working with a relatively small data set, we've only got 4 different classes, we've only got 1,000 data points, we'll keep it small as well, but you could change this. Remember, you can change any of these because they're hyperparameters. For the output layer shape, well, hence, again, for the hidden layer class classification, we've got this. For the input layer shape, we need to define the in features. So how many in features do we have? For the hidden layers, well, we could set this to whatever we want, but we're going to keep it nice and simple for now. For the number of neurons per hidden layer, again, this could be almost whatever we want, but because we're working with a relatively small data set, we've only got 4 different... For the number of neurons, so how many in features do we have? For the hidden layers, well, we could set this to whatever we want, but we're going to keep it nice and simple for now. For the number of neurons per hidden layer, again, this could be almost whatever we want, but because we're working with a relatively small data set, we've only got 4 different classes, we've only got 1,000 data points, we'll keep it small as well, but you could change this. Remember, you can change any of these because they're hyperparameters. For the output layer shape, well, how many output features do we want? We need 1 per class. How many classes do we have? We have 4 clusters of different dots here, so we'll need 4 output features. And then if we go back, we have an output activation of softmax. We haven't seen that yet. And then we have a loss function. Rather than binary cross entropy, we have cross entropy. And then optimizer as well is the same as binary classification. 2 of the most common SGDs, the stochastic gradient descent, or the atom optimizer. But of course, the torch.optim package has many different options as well. So let's push forward and create our first multi-class classification model. First, we're going to create, we're going to get the habit of creating device agnostic code. And we'll set the device here, equals CUDA. Nothing we haven't seen before. But again, we're doing this to put it all together so that we have a lot of practice. Is available, else CPU. And let's go device. So we should have a GPU available. Beautiful, CUDA. Now, of course, if you don't, you can go change runtime type, select GPU here. That will restart the runtime. You'll have to run all the code
just
before this.
To the CPU, but yeah, we can use CUDA. I mean, we can use a GPU if needed.
Cell as well, but I'm going to be using a GPU. You don't necessarily need one because our dataset's quite small and our models aren't going to be very large, but we set this up so we have device agnostic code. And so let's build a multi-class classification model. Ooh, look at us go. Just covering all of the foundations of classification in general here. And we now know that we can combine linear and nonlinear functions to create neural networks that can find patterns in almost any kind of data. So I'm going to call my class here blob model, and it's going to, of course, inherit from nn.module. And we're going to upgrade our class here. We're going to take some inputs here, and I'll show you how to do this. If you're familiar with Python classes, you would have already done stuff like this, but we're going to set some parameters for our models, because as you write more and more complex classes, you want to take inputs here. And I'm going to pre-build or preset the hidden units parameter to 8. Because I've decided, you know what, I'm going to start off with 8 hidden units, and if I wanted to change this to 128, I could. But in the constructor here, we've got some options. So we have input features. We're going to set these programmatically as inputs to our class when we instantiate it. The same with output features as well. And so here, we're going to call self, oh no, super, sorry, I always get this mixed up, .init, and underscore, beautiful. So we can do a doc string here as well. So let's write in this. Initializes multi-class classification. If I could spell classification model. Oh, this is great. And then we have some args here. This is just a standard way of writing doc strings. If you want to find out, this is Google Python. Oh, this is great. And then we have some args here. This is just a standard way of writing doc strings. If you want to find out, this is Google Python docstring guide.
I've written
there we go, Google Python style guide. This is where I get mine from. You can scroll through this. This is just a way to write Python code. Yeah, there we go. So we've got a little sentence saying what's going on. We've got args, we've got returns, and we've got errors if something's going on. So I highly recommend checking that out. Just a little tidbit. So this is if someone wants to use our class later on. They know what the input features are. Input features, which is an int, which is number of input features to the model. And then, of course, we've got output features, which is also an int, which is number of output features of the model. And we've got the red line here.
Why it doesn't? Yeah, there we go.
here is telling us we've got something wrong, but that's okay. And then the hidden features, oh, well, this is number of output classes for the case of multi-class classification. And then the hidden units, int, and then number of hidden units.
But that's not an art, that's a quark. So I guess Daniel is yeah, skipping that out. And
layers.
I mean,
and then the default
fine.
is 8. Beautiful. And then under that, we'll just do that. Is that going to fix itself? Yeah, there we go. We could put in what it returns, whatever it returns, and then an example use case, but I'll leave that for you to fill out if you like. So let's instantiate some things here. What we might do is write self.linear layer stack, self.linear layer stack, and we will set this as nn.sequential. Oh, we haven't seen this before, but we're just going to look at a different way of writing a model here. Previously, when we created a model, what did we do? Well, we instantiated each layer as its own parameter here, and then we called on them one by one, but we did it in a straightforward fashion. So that's why we're going to use sequential here to just step through our layers. We're not doing anything too fancy, so we'll just set up a sequential stack of layers here, and we'll call all that sequential just steps through, passes the data through each one of these layers one by one, and because we've set up the parameters up here, input features can equal to input features, and output features, what is this going to be? Is this going to be output features, or is this going to be hidden units? It's going to be hidden units because it's not the final layer. We want the final layer to output our output features. So input features, this will be hidden units because remember, the subsequent layer needs to line up with the previous layer. Output features, we're going to create another one that outputs hidden units, and then we'll go nn.linear. In features equals hidden units because it takes the output features of the previous layer. So as you see here, the output features of this feeds into here, the output features of this feeds into here, and then finally this is going to be our final layer. We'll do 3 layers. Output features equals output features. Wonderful. So how do we know the values of each of these? Well, let's have a look at xtrain.shape and ytrain.shape.
So we are building a model with 3 layers.
So in the case of x,
yes. Yep. So it can be output features. So why is this? Why is this giving me an error though? Self is not defined. That should fix it.
we have 2 input features. In the case of y, well, this
And I
is a little confusing as well because y is a scalar. But what do you think?
now what? That yeah,
The values for y are going to be? Well, let's go np, or is there torch.unique? I'm not sure. Let's find out together, hey? Torch unique, 0 and 1, y train. Oh, we need y input features. In the case of y, well, this is a little confusing as well because y is a scalar. But what do you think the values for y are going to be? Well, let's go np, or is there torch.unique? I'm not
Yeah, we need to convert X into logits and then convert it into labels or predictions.
sure. Let's find out together, hey? Torch unique, 0 and 1, y train. Oh, we need y blob train. That's right, blog. I'm too used to writing blob. And we need blob.
Oh, yeah, that's right. That's what I was wondering. Hey, didn't we create a blob, you know, training set before? Why are we using the previous one right now?
Blob train, but I believe it's the same here. And then blob. There we go. So we have 4 classes. So we need
Oh, torch.unique gives just the unique items, huh? That's good to know. Why blob thing?
an output features value of 4. And now if we wanted to add nonlinearity here, we could put it in between our layers here like this.
Oh yeah, because this time it's just not 0 and 1 because we have red, yellow, blue, and I guess was it green? No, I guess it's light blue.
But I asked the question before, do you think that this data set needs nonlinearity? Well, let's leave it in there to begin with. And one of the challenges for you... Oh, do we need commas here? I think we need commas here.
It should be. I don't think it needs it. It's a trick question because I guess if we provide ReLU, it would be more. Well, I'm predicting that the accuracy would be more with ReLU, but even without ReLU, it would be fine. Is my prediction. Let's see what comes out of that. Let's see what the actual result is.
One of the challenges for you will be to test the model with nonlinearity and without nonlinearity. So
we'll surely do that once we make the...
Let's just leave it in there for the time being. What's missing from this? Well, we need a forward method. So def forward self x. What can we do here? Well, because we've created this as a linear layer stack using nn.sequential, we can just go return linear layer stack and pass it x. And what's going to happen? Whatever input goes into the forward method is just going to go through these layers sequentially. Oh, we need to put self here.
That's for linear layer stack. Yeah. Forward self there. And now we'll just return self.linear layer stack x.
Because we've initialized it in the constructor. Beautiful. And now let's create an instance of blob model and send it to the target device. We'll go model 4 equals blob model. And then we can use our input features parameter, which is this one here. And we're going to pass it a value of what? 2. And then output features. Why? Because we have 2 x features. Now the output feature is going to be the same as the number of classes that we have. 4. If we had 10 classes, we'd set it to 10. So we'll go 4. And then the hidden units is going to be 8 by default. So we don't have to put this here, but
let's just do what was it? Num features, right? Let's just
put it there anyway.
keep it.
And then of course we're going to send this to the device, and then we're going to go model 4. What do we get wrong here? Unexpected.
Okay. Output features.
Keyword argument. Output features. Did we spell something wrong? No doubt we've got a spelling mistake. Output features. Output features? Oh, out features. Ah.
Oh, okay. Gotcha.
That's what we needed. Out features, not output. I got a little confused there. Okay. There we go. Okay, beautiful. So just recall that the parameter here for nn.linear, did you pick up on that? Is out features, not output features. Output features, a little confusing here, is our final layout. Output layers, number of features there. So we've now got a multi-class classification model that lines up with the data that we're using. So the shapes line up. Beautiful. Well, what's next? Well, we have to create a loss function and, of course, a training loop. So I'll see you in the next few videos, and let's do that together. Welcome back. In the last video, we created our multi-class classification model. And we did so by subclassing nn.module, and we set up a few parameters for our class constructor here, so that when we made an instance of the blob model, we could customize the input features, the output features. Remember, this lines up with how many features X has, and the output features here lines up with how many classes are in our data. So if we had 10 classes, we could change this to 10, and it would line up. And then if we wanted 128 hidden units, well, we could change that. So we're getting a little bit more programmatic with how we create models here. And as you'll see later on, a lot of the things that we've built in here can also be functionalized in a similar manner. But let's keep pushing forward. What's our next step? If we build a model, if we refer to the workflow, you'd see that we have to create a loss function and an optimizer for a multi-class classification model. And so what's our option here for creating a loss function? Where do we find loss functions in Pytorch? I'm just going to get out of this, and I'll make a new tab here. And if we search torch.nn, because torch.nn is the basic building blocks for graphs, in other words, neural networks, where do we find loss functions? Here we go. Beautiful. So we've seen that L1 loss or MSE loss could be used for regression predicting a number, and I'm here to tell you as well that for classification, we're going to be looking at cross-entropy loss. Now, this is for multi-class classification. For binary classification, we work with BCE loss. And of course, there's a few more here, but I'm going to leave that as something that you can explore on your own. Let's jump into cross-entropy loss. So what do we have here? This criterion computes. Remember, a loss function in Pytorch is also referred to as a criterion. You might also see loss function referred to as cost function, C-O-S-T, but I call them loss functions. So this criterion computes the cross-entropy loss between input and target. Okay, so the input is something, and the target is our target labels. It's useful when training a classification problem with C classes. There we go. So that's what we're doing. We're training a classification problem with C classes. C is a number of classes. If provided, the optional argument weight should be a 1D tensor assigning a weight to each of the classes. So we don't have to apply a weight here, but why would you apply a weight? Well, it says, if we look at weight here, This is particularly useful when you have an unbalanced training set. So just keep this in mind as you're going forward. If you wanted to train a data set that has imbalanced samples, in our case, we have the same number of samples for each class, but sometimes you might come across a data set with maybe you only have 10 yellow dots, and maybe you have 500 blue dots, and only 100 red and 100 light blue dots.
Right.
So you have an imbalanced data set. So that's where you can come in and have a look at the weight parameter here. But for now, we're just going to keep things simple. We have a balanced data set, and we're going to focus on using this loss function. If you'd like to read more, please, you can read on here. And if you wanted to find out more, you can go, what is cross entropy loss? And I'm sure you'll find a whole bunch of loss functions. There we go. There's the ML cheat sheet. I love that, the ML glossary. That's one of my favorite websites.
Again, we'll check out all the math later. Like, we'll have a separate stream or video for that.
On that website, Wikipedia, Machine Learning Mastery is also another fantastic website. But you can do that all in your own time. Let's code together, eh? We'll set up a loss function. Oh, and one more resource before we get into code is that we've got the architecture, well, the typical architecture of a classification model. The loss function for multi-class classification is cross entropy, or torch.nn.cross entropy loss. Let's code it out. If in doubt, code it out. So create a loss function for multi-class.
Hey, we got a message on chat now. Cheap viewers. It's I guess that's a bot maybe.
Classification. And then we go loss fn equals nn dot cross entropy loss. Beautiful. And then we want to create an optimizer. Create an optimizer.
Alright, let's create our loss function.
For multi-class classification. And now the beautiful thing about optimizers is they're quite flexible. They can go across a wide range of different problems. So the optimizer, so two of the most common, and I say most common because they work quite well across a wide range of problems. So that's why I've only listed two here. But of course, within the torch.optim module, you will find a lot more different optimizers.
Again, we're gonna use the stochastic gradient descent or random gradient descent.
But let's stick with SGD for now, and we'll go back. We'll go optimizer equals torch.optim for optimizer, SGD for stochastic gradient descent. The parameters we want our optimizer to optimize, model 4, we're up to our fourth model already, oh my goodness. Model 4.parameters, and we'll set the learning rate to 0.1. Of course, you can change the learning rate if you wanted to. In fact, I'd encourage you to see what happens if you do.
Not really, it's been some days since we started this stream.
Is a hyperparameter. I'm very right code that I am at spelling. You can change. Wonderful. So we've now got a loss function and an optimizer for a multi-class classification problem. What's next? Well, we could start to building a training loop. We could start to do that, but I think we have a look at what the outputs of our model are. So more specifically, so getting prediction probabilities for a multi-class Pytorch model. So my challenge to you before the next video is to have a look at what happens if you pass xblob test through a model. And remember, what is a model's raw outputs? What is that referred to as?
Logits. Basically, Daniel is telling us to convert the logits into labels or prediction probabilities. So let's do that. So y logits is gonna be what? It's gonna be model 4. We're gonna put our testing set. If you're gonna put our testing set, you know what? Let's start eval mod. And we have our logits. Now y predictions is gonna be, what's that gonna be, you ask? It's gonna be, you're gonna round it after, round all the individual elements after passing it through the sigmoid function. That's gonna be our predictions. Let's print out y logits, the first 10 elements, and y predictions, the first 10 elements. And I know there isn't any use yet, but let's just print out the y blob test, the first 10 elements. It's gonna be random, so I don't, anyhow. So what do we have here? I expect that. What did we do wrong here? We got a tensor. Okay. So let's look at this one by one. The logits is looks like this. Okay, all right. 2, I mean, it did round it off, but that doesn't look like our blob
I'll
test.
let you have a think about that
Do
for
we
the next
need
video. I'll see you there.
to? I'm not sure.
Welcome back. In the last video, we created a loss function and an optimizer for our multi-class classification model. And recall, the loss function measures how wrong our model's predictions are, and the optimizer updates our model parameters to try and reduce the loss. So that's what that does. And I also issued the challenge of doing a forward pass with model 4, which is the most recent model that we created. And oh, did I just give you some code that wouldn't work? Did I do that on purpose? Maybe, maybe not. You'll never know. So if this did work, and oh, did I just give you some code that wouldn't work? Doing a forward pass with model 4, which is the most recent model that we created. And oh, did I just give you some code that wouldn't work? Did I do that on purpose? Maybe, maybe not. You'll never know. So if this did work, what are the raw outputs of our model? Let's get some raw outputs of our model. And if you recall, the raw outputs of a model are called logits. So we've got a runtime error. Expected all tensors to be on the same device. Oh, of course. Why did this come up? Well, because if we go next, model 4 dot parameters, and if we check device, what happens here? Oh, we need to bring this in. Our model is on the CUDA device, whereas our data is on the CPU still. Can we go X? Is our data a tensor? Can we check the device parameter of that? I think we can. I might be proven wrong here. Oh, it's on the CPU. Of course we're getting a runtime error. Did you catch that one? If you did, well done. So let's see what necessarily have to do this because it's just test, but it's a good habit. Oh, y preds equals, what do we get? Y preds, and maybe we'll just view the first 10. What do we get here? Oh my goodness, a whole bunch of numbers on a page. Is this the same format as our data or our test labels? Let's have a look. No, it's not. Okay. Oh, we need y blob test. Excuse me. I'm going to make that mistake a fair few times here. So we need to get this into the format of this. How can we do that? Now, I want you to notice one thing as well, is that we have one value here.
Although, what's happening here? I didn't get that. I didn't get the... Like, my predictions are different from what's being shown there. So maybe I was wrong. Let's see. We are passing the X-blob test itself. I mean, Daniel is calling this as by like these are he's calling it directly by as by predictions. Okay. It is different. So maybe we did something wrong there. Let's see. By blob train, by blob test. Just run that again. And run this again. What did we do wrong here?
Per one value, except that this is actually 4 values. Now, why is that? We have 1, 2, 3, 4. Well, that is because we set...
But I have only 2 values. Oh, okay. Let's see. When you create the model, our number of input features is supposed to be 4, not 2. Alright, there we go. We solved that, I believe.
Set the out features up here.
And
our model...
wait, not perfect. Math 1 and math 2 should not be multiplied. What? Let's see. No, he has given it us too.
outputs 4 features per sample. So each sample right now has 4.
What is num features? Oh, of course, of course. This is... I meant num class here, didn't I? Num classes.
4 numbers associated with it. And what are these called?
Let's just do it the quote-unquote correct way or the better way so that we make it a habit. So short inference mode.
These are the logits. Now, what we have to do here, so let's just write this down. In order to evaluate and train and test our model, we need to convert our model's outputs which are logits, to prediction probabilities, and then to prediction labels. So we've done this before, but for binary classification. So we have to go from logits to predprobs to pred labels. All right, I think we can do this. So we've got some logits here. Now, how do we convert these logits to prediction probabilities?
We can't use sigmoid here, can we? Because sigmoid will just round off to 0 and 1. Yeah.
Well, we use an activation function. And if we go back to our architecture, what's our output activation here? For a binary classification, we use sigmoid. But for multi-class classification, these are the two main differences between multi-class classification and
Softmax, huh?
binary classification. One uses softmax, one uses cross entropy. And it's going to take a little bit of practice to know this off by heart. It took me a while, but that's why we have nice tables like this, and that's why we write a lot of code together. So we're going to use the softmax function here to convert our logits, our model's raw outputs, which is this here, to prediction probabilities. And let's see that. So convert our model's logit outputs to prediction probabilities. So let's create y pred probs. So I like to call prediction probabilities pred probs for short. So torch.softmax, and then we go y logits, and we want it across the first dimension. So let's have a look. If we print y logits, we'll get the first 5 values there, and then look at the conversion here. Y logits, or y pred probs. That's what we want to compare. Pred probs 5. Let's check this out. Oh, what did we get wrong here? Y logits. Do we have y logits? Oh no, we should change this to y logits because really that's the raw output of our model here.
Yeah, that's what I was wondering. Why did we call it predictions immediately? Yeah, I guess that answers that.
Logits, let's rerun that. Check that. We know that these are different to these, but we ideally want these to be in the same format as these. Our test labels, these are our model's predictions, and now we should be able to convert. There we go. Okay, beautiful. What's happening here? Let's just get out of this. And we will add a few code cells here so we have some space. Now, if you wanted to find out what's happening with torch.softmax, what could you do? We could go torch softmax, see what's happening. Softmax. Okay.
It applies this form.
Okay, so here's the function that's happening. We replicated some nonlinear activation functions before. So if you wanted to replicate this, what could you do? Well, if in doubt, code it out. You could code this out. You've got the tools to do so. We've got softmax to sum x input takes the exponential of x, so torch exponential over the sum of torch exponential of x. So I think you could code that out if you wanted to, but let's for now just stick with what we've got. We've got some logits here, and we've got some softmax, some logits that have been passed through the softmax function. So that's what's happened here. We passed our logits as the input here, and it's gone through this activation function. These are prediction probabilities. And you might be like, Daniel, these are still just numbers on a page, but you also notice that none of them are negative. Okay, and there's another little tidbit about what's going on here. If we sum one of them up, let's get the first one. Will this work? And if we go torch.sum, what happens? Oh, they all sum up to 1, so that's one
Huh. That's pretty cool.
of the effects of the softmax.
Oh, so it's I see. It's like out of 100% or out of 1, what percentage is it a blue dot, red dot, green? Okay, so yeah, that makes sense. Yeah.
Softmax function. And then if we go torch.max of y pred probs, so this is a prediction probability.
Argmax probably is what we'll use.
For multi-class, you'll find that for this particular sample here, the 0th sample, this is the maximum number.
Yeah.
And so our model, what this is saying is our model is saying, this is the prediction probability, this is how much I think it is class 0, this number here, it's in order. This is how much I think it is class 1. This is how much I think it is class 2. This is how much I think it is class 3. And so we have one value for each of our 4 classes.
Yeah.
A little bit confusing because it's 0th indexed, but the maximum value here is this index. And so how would we get the particular index value of whatever the maximum number is across these values? Well, we can take the argmax, and we get tensor 1. So for this particular sample, this one here, our model, and these guesses or these predictions aren't very good. Why is that? Well, because our model is still just predicting with random numbers. We haven't trained it yet. So this is just random output here, basically. But for now, the premise still remains that our model thinks that for this sample, using random numbers, it thinks that index 1 is the right class, or class number 1 for this particular sample. And then for this next one, what's the maximum number here? I think it would be the 0th index. And the same for the next one. What's the maximum number here? Well, it would be the 0th index as well. But of course, these numbers are going to change once we've trained our model. So how do we get the maximum index value of all of these? So this is where we can go convert our model's prediction probabilities to prediction labels. So let's do that. We can go ypreds equals torch.argmax on ypred probs, and if we go across the first dimension as well. So now let's have a look at ypreds. Do we have prediction labels in the same format as our y lob test? Beautiful. Yes, we do. Although many of them are wrong.
That makes sense. Now it makes sense why zero indexing is used, like to assign to the classes. Why it starts from zero, you know. Okay, so I press props and we're just gonna let's just do it in a new line.
As our Y blob test. Beautiful. Yes, we do. Although many of them are wrong, as you can see. Ideally, they would line up with each other, but because our model is predicting or making predictions with random numbers, so our model hasn't been trained, all of these are basically random outputs. So hopefully once we train our model, it's going to line up, the values of the predictions are going to line up with the values of the test labels. But that is how we go from our model's raw outputs to prediction probabilities to prediction labels for a multi-class classification problem. So let's just add the steps here. Logits, raw output of the model. Pred probs, to get the prediction probabilities, use torch.softmax, or the softmax activation function. Pred labels, take the argmax of the prediction probabilities. So we're going to see this in action later on when we evaluate our model. But I feel like now that we know how to go from logits to prediction probabilities to pred labels, we can write a training loop. So let's set that up. 8.5, create a training loop and testing loop for a multi-class Pytorch model. This is so exciting. I'll see you in the next video. Let's build our first training and testing loop for a multi-class Pytorch model. And I'll give you a little hint. It's quite similar to the training and testing loops we've built before, so you might want to give it a shot. I think you can. Otherwise, we'll do it together in the next video.
I guess let's do it ourselves and see what we get to. So now it makes sense why you have prediction probabilities and then we convert it into labels. All right. As always, let's set the number of epochs. 1000 should be fine, I guess. And let's send everything onto the device. Make it device agnostic code, as Daniel would put it. So X blob test. And we have Y blob test equal to, now copy this, put it up here. I'm gonna put this to the wrong device. There we go. And we're just gonna do for epoch in range of epochs. What was I supposed to do now? Oh yeah. Remember the universal Python song? Yes. Anyway, mod switch to training mode first of all. Make that a habit. And then we're gonna do the forward pass. So assign that to Y logits. We're gonna give it by blob train, and not by blob train, X blob train. And then we are gonna calculate the prediction probabilities. That's gonna be what? That's gonna be torch.softmax. Right? Yeah, torch.softmax. And we're gonna give it our Y logits. What does dimension do again? What does, oh, it just tells it to use the values in the first dimension, I believe. Let's see if that logic is right. Yeah, that's what it does. So I have Y logits here. We can just squeeze it too, I believe, right? If we just squeeze it, we don't need the dimensions anymore. Yep. Let's try that out. You know, we need a variety in life and variety in code as well. Anyhow, so we have our prediction probabilities. Now to convert that to our labels or actual predictions, we're just gonna apply our argmax on the y prediction probabilities. Great, so now that's done. What are we supposed to do now? Calculate the loss, right? So loss is just gonna be the loss function that we have. Now let's check the documentation. Although wait a second, listen. Last time we used, what did we use? We used BC with logit loss, that loss function, right? So let's just check out cross and repeat loss first, and then I think we can just pass the activated. We don't need to pass the logits here. We just give it our final predictions instead. Wait a second, is that what we do? Because yeah, I think that is what we should do. Anyway, we'll find out. Then we're gonna do optimizer.zero grad so it doesn't accumulate gradients. And what are we gonna do next, you ask? We're gonna use back propagation on our loss, and then we're just gonna do optimizer.step so that our model learns. We can, let's do the testing.
Yeah.
So
The raw output
let's
is
just
into
check
prediction
out the
labels
video
by taking
first.
the argmax, which returns the index of where the maximum value occurs in the prediction values. The print is 1 for this one. But now we're going to the data on the page, not guarantee complete determinism, which means the same output. But we're going to try. The direction is more important. Set number of epochs. We're going to go epochs. How about we just do 100? I reckon we'll start with that. We can bump it up to 1,000 if we really wanted to. Let's put the data to the target device. What's our target device? Well, it doesn't really matter because we've set device agnostic code. So whether we're working with a CPU or a GPU, our code will use whatever device is available. I'm typing blog again. So we've got X blob train, Y blob train. This is going to go where? It's going to go to the device. And Y blob train to device. And we're going to go X blob test, and then Y blob test equals X blob test to device. Otherwise, we'll get device issues later on, and we'll send this to device as well. Beautiful. Now, what do we do now? Well, we loop through data. Loop through data. So for an epoch in range epochs, for an epoch in a range epochs. I don't want that autocorrect. Come on, Google Colab, work with me here. We're training our first multi-class classification model. This is serious business. No, I'm joking. It's actually quite fun. So model4.train. And let's do the forward pass. I'm not going to put much commentary here because we've been through this before, but what are the logits? The logits are raw outputs of our model. So we'll just go X blob train and X test. I didn't want that. X blob train. Why did that do that? I need to turn off autocorrect in Google Colab. I've been saying it for a long time. Y pred equals torch.softmax. So what are we doing here? We're going from logits to prediction probabilities here. So torch softmax Y logits across the first dimension. And then we can take the argmax of this and dim equals 1. In fact, I'm going to show you a little bit of, I've written blog here. Maybe autocorrect would have been helpful for that. A little trick, you don't actually have to do the torch softmax. The logits, if you just took the argmax of the logits, is a little test for you. Just take the argmax of the logits and see, do you get the same similar outputs as what you get here? So I've seen that done before.
Just take the argmax of the load.
But for completeness, we're going to use the softmax activation function because you'll often
If you take the argmax of the logit,
see this in practice. And now what do? We calculate the loss. So the loss Fn, we're going to use categorical cross entropy here, or just cross entropy loss. So if we check our loss function, what do we have? We have cross entropy loss. We're going to compare our model's logits to Y blob train. And then what are we going to do? We're going to calculate accuracy because we're working with a classification problem. It'd be nice if we had accuracy as well as loss. Accuracy is one of the main classification evaluation metrics. Y pred equals Y pred. Y pred.
oh yeah, we did not calculate accuracy. So that
And now what do? Well, we have to zero grad the optimizer zero grad, then we go last backward, and then we step the optimizer step, step, step. So none of these steps we haven't covered before. We do a forward pass, we calculate the loss and any evaluation metric we choose to do so. We zero the optimizer, we perform backpropagation on the loss, and we step the optimizer. The optimizer will hopefully behind the scenes update the parameters of our model to better represent the patterns in our training data. And so we're going to go testing code here. What do we do for testing code? Well, for inference code, we set our model to eval mode. That's going to turn off a few things behind the scenes that our model doesn't need, such as dropout layers, which we haven't covered, but you're more than welcome to check them out if you go torch mn. Dropout layers, do we have dropout? Dropout layers, beautiful. And another one that it turns off is match norm, beautiful. And also, you could search this. What does model.eval do? And you might come across Stack Overflow question, one of my favorite resources. So there's a little bit of extracurriculum, but I prefer to see things in action. So with torch inference mode, again, this turns off things like gradient tracking and a few more things, so we get as fast as code as possible.
Let's do that real quick.
Because we don't need to track gradients when we're making predictions. We just need to use the parameters that our model has learned. We want xblob test to go to our model here for the test logits, and then for the test spreads, we're going to do the same step as what we've done here. We're going to go torch.softmax on the test logits across. The first dimension.
We can just squeeze this, right? That should anyway result in him taking the first dimension.
And we're going to call the argmax on that to get the index value of where the maximum prediction probability value occurs. We're going to calculate the test loss or loss function. We're going to pass in what? The test logits here. Then we're going to pass in y blob test. Compare the test logits. Behind the scenes, our loss function is going to do some things that convert the test logits into the same format as our test labels and then return us a value for that. Then we'll also calculate the test accuracy here by passing in the y true as y blob test. And we have the y pred equals y pred. Wonderful. And then what's our final step? Well, we want to print out what?
Ning.
What's happening? Because I love seeing metrics as our model trains. It's one of my favorite things to watch. If we go if epoch, let's do it every 10 epochs because we've got 100 so far, equals 0. Let's print out a nice f string with epoch. And then we're going to go loss. What do we put in here? We'll get our loss value, but we'll take it to 4 decimal places, and we'll get the training accuracy, which will be ac. And we'll take this to 2 decimal places, and we'll get a nice percentage sign there. And we'll go test loss equals test loss, and we'll go there. And finally, we'll go test ac at the end here. Test ac. Now, I'm sure by now,
What is bit capital?
we've written a fair few of these. You're either getting sick of them, or you're like, wow, I can actually do the steps through here. And so don't worry, we're going to be functionizing all of this later on, but I thought I'm going to include them as much as possible so that we can practice as much as possible together. So you ready? We're about to train our first multi-class classification model. In 3, 2, 1, let's go. No typos.
Go.
Oh, of course. What did we get wrong here?
Because code always runs on the first try. Okay. Let's see. Not implemented for plot.
Oh, this is a fun error. Runtime error. NLL lost forward reduced CUDA kernel to the index not implemented for float. Okay, that's a pretty full-on bunch of words there. I don't really know how to describe that, but here's a little hint. We've got float there. So we know that float is what? Float is a form of data. It's a data type. So potentially, because that's our hint, we said not implemented for float. So maybe we...
Although what did I get? Yes, we got tensor. Expected. Okay. Didn't. So I guess we can't squeeze it. We have to put our dimensions as on. All right. Let's see. Let's see. Well, yeah, there we go. Although, yeah, we don't need to squeeze this.
2D index not implements. What did we get wrong here? Oh.
Let's run this now. Cross entropy target. Of course. We need to pass in our y train, y blob. Autocomplete. Yeah, there we go. Autocomplete finally sprung up. Now I press to do the same thing here. Yeah, they already done that. And what do we have here? Which line is that?
This is a fun error. Runtime error. NLL lost forward reduced CUDA kernel to the index not implemented for float. Okay, that's a pretty full-on bunch of words there. I don't really know how to describe that, but here's a little hint. We've got float there. So we know that float is what? Float is a form of data. It's a data type. So potentially, because that's our hint, we said not implemented for float, so maybe we've got something wrong up here. Our data is of the wrong type. Can you see anywhere where our data might be the wrong type? Well, let's print it out. Where's our issue? Here. Y logits. Y blob train. Okay. Y blob train and Y logits. What does Y blob train look like? Y blob train. Okay. And what's the D type here? Float.
Okay. Let's do it. Let's do it the normal way. So so I want to know what the D type here is for both of these. See what the data type is. This should be widespread, right? Maybe even widespread is of in64.
Float. Okay. So it's not implemented for float. Maybe we have to turn them into a different data type. What if we went type torch long tensor? What happens here? Expected all tensors to be on the same device, but found at least 2 devices. Oh my goodness, what have we got wrong here? Type torch long tensor.
Expected floating type for target with class probabilities got long. Okay, in that case, let's change this one over here to be torch dot plot. Is that running or is that stuck? What's happening at the doubt? Element 0 of tensors. Gosh, Daniel wasn't kidding when he meant that shapes and data types are the most common errors found with Pytorch. Alright, what do we have here? Runtime error. Element 0 of tensors does not require grad and does not have a grad function. Did I mess up the zero grad maybe. Optimize zero grad lows backward. Optimize a step, step, step. Look at me. I learned this song already. Okay. What's the issue here? Element 0 of tensors does not require grad and does not have a grad function.
Friends, guess what? I found it. And so it was to do with this pesky little data type issue here. So if we run this again, and now this one took me a while to find, and I want you to know that behind the scenes, even though, again, this is a machine learning cooking show, it still takes a while to troubleshoot code, and you're